Hey class, Adam Ward here. Want to walk through the Hagen-Poiseuille derivation today. Uh, so this is going to be applied to fully developed laminar flow in a horizontal pipe or tube. So what we're starting with here is just a conceptualization of discharge moving through a circular conduit. In blue there, I've drawn a typical velocity profile, including those no-slip boundary conditions where velocity equals 0 at the pipe walls. In orange over on the right, I'm drawing the shear stress profile, where the idea here is that the vertical line shear stress would be 0, and it is increasing linearly from no shear stress at the pipe center line to some shear stress at the wall, or TW we'll call it eventually, moving up or down from the center line. So for this derivation, we're going to isolate a small cylinder of fluid in the middle of the pipe, shown in red, radius R and length L. So we're going to analyze this by using a sum of the forces in the x direction. And of course, force equals mass times acceleration. But if we're dealing with steady flow, acceleration is 0. So the sum of the forces in the x must be 0. So let's think about a free body diagram here, and we're only going to keep track of x-directed or horizontal forces in this case. So for our cylinder of fluid, we might have a pressure force on the left, and of course that's acting on the area on the left. Similarly, a pressure force acting on the area from the right. And then where the fluid is in contact with the pipe wall, so all the way around the inside of the pipe walls, we're going to have a shear stress multiplied by the area that's in contact with the fluid. Excuse me. All right, so let's see what we can do there. We've got our sum of the forces in the x equals 0, and you can see that I've now added the three terms: pressure on the left, pressure forces on the right, and shear stress. We'll deal with areas first. The left and right-hand sides are a circle, so pi times the radius squared. And the area for shear stress, what I want you to picture is that we've taken that pipe and we've unrolled it. So it was length L, and the height of that rectangle that we unrolled it to is the circumference of that circle, or 2 pi r. So the shear stress acts over a total area of length multiplied by 2 pi r. Finally, the pressure on the left and right. We don't know what the pressure is, but we're going to assume that the pressure on the right could be described as the pressure on the left minus any change in pressure that happened along the way. So when we put those all together, we get the equation shown here. And you can see that I've gone ahead and just plugged in those definitions for areas as well as that pressure drop. We've replaced it in the middle term. So we can cancel a few things out. In red, you can see I'm canceling out the pressure on the left-hand side. Each term has a pi, so we could go through and divide by pi. And similarly, each term has more than at least one r, so we can remove r entirely from the right hand and remove those squareds from the first and second terms. So simplify that equation from above, organize it with a little bit of algebra, and we find the pressure drop per unit length, or the head loss, is equal to 2 times the shear stress divided by the radius. So the pressure drop is being offset by the shear stresses. Okay, so from there, we're going to deal with Ta, and you can see that part of my writing's already built in, but we'll roll with it. So I want you to picture the center line of the pipe here that I've drawn dashed, and the wall and the solid line. And again, we're going to manifest this idea of a linear shear stress profile, meaning this is a Newtonian fluid. That shear relationship grows linearly. Okay, so because that's a linear relationship, we can describe it relatively easily here. The shear stress at any radius r can be described as 2 times the shear stress at the wall, TW, times the radius divided by the diameter of this pipe. So what we're doing there is just manifesting an equation to describe that linear relationship that we've drawn on the left-hand side. And of course, we know a couple of places that we use to derive this from. Shear stress is 0 when radius is 0. That's the pipe center line. and shear stress is TW when we're at the wall, when R is equal to D over 2. Okay, so taking the equation we had on the prior slide, and we're going to go ahead and plug in our new definition for shear stress. You can see that I'm canceling the R in the numerator and the denominator there. And so we're left with the pressure drop on the left is equal to 4 times the length of the pipe L. You can see I moved it to the right-hand side for the time being, times that wall shear stress divided by D. So this lets us relate the pressure drop on the left to the pipe geometry and the wall shear stress. Now, wall shear stress is not a particularly easy thing for us to measure, but we do know that it should be related to velocity. The faster the fluid is moving, the higher that shear stress should be, and that should grow linearly. So on the next slide, we're going to deal with that shear stress term and see if we can't describe it with velocity instead. So for a Newtonian fluid, this is our fundamental conceptualization for shear stress, tau. It's equal to minus the viscosity of the fluid times du dr. So how fast the x-directed velocity changes as we move in the radial dimension. So u is the x-directed velocity here. And so we can take the equation we had on the previous slide. We can substitute this definition for shear stress. And we can rearrange just a little bit. I'm taking that D in the denominator, replacing it with a 2 times R, just to get the D's out of the way. So everything will be in variables of R for radius. Okay, from there, we're going to separate variables. So I'm going to keep the du on one side, and I'm going to get all of the constants plus the R and the dr on the right. So that's just an algebraic manipulation of the previous step. From there, we're going to integrate both sides of this equation. And on the left-hand side, we get the velocity. On the right-hand side, we've got those constants times 1/2 r squared, and then plus C1, that constant of integration. Now we know something in this problem. We know that velocity should be 0 when the radius is equal to diameter over 2. In other words, velocity is 0 at the wall of the pipe. We're enforcing that no slip boundary condition over at the wall. And so when we do that, we can calculate a value for C1. We get delta P over 16 mu L multiplied by diameter squared. Okay, so put together what we know so far, and we've got an equation describing velocity as a function of radius. We've got that constant of integration, and we've got that the r squared term there as well. So this relates pressure drop, pipe diameter, and velocity to one another. And just as a quick aside, one interesting fact here, if we think about what happens when the radius is equal to 0, in other words, what happens right at the pipe center line, everything in brackets would drop away. And what you would end up with is just that leading constant. The velocity at the center line is equal to the pressure drop times diameter squared divided by 16 mu L. So that leading set of constants is describing the velocity at the pipe center line, and what's in the brackets is essentially correcting for that as you move away from the center line and out toward the boundary. That gives us that nice parabolic velocity profile from the center line as we move outward as well. Okay, so we've related this to average velocity and the geometry of the problem, but it's a lot more convenient to express this in relation to discharge. We know that discharge area and velocity are all going to be related to one another. So the next couple steps here are going to be about velocity, or excuse me, about velocity and discharge. So what I've written here, discharge is equal to the integral of velocity. So UR, that's the velocity at any coordinate r, multiplied by 2 pi r, so that's the circumference of the circle, multiplied by dr, the radius. So what we're doing is making sort of a bunch of concentric donuts, if you want to think about it that way, and adding those all up. And we're integrating from the center line to the pipe wall. Now, One thing that we can do here is we can express this a little differently. Instead of using that description of velocity at radius r, we can substitute in that description using the centerline velocity, and you can see the brackets still remain from what I have written in black. So we can go ahead and apply that integral to that problem. So we've separated out the two terms in brackets now, the r dr multiplied by 1 going first, the r dr multiplied by the 2r over d squared on the right-hand term there. And finally, we can go ahead and perform the integration. And when we do that, you can see we arrive at the following equation. And we've basically integrated those two terms. And just going through and doing a little bit of simplification here. Sorry, you get the equation that I've written on the right-hand side. And if you're asking yourself, hey, I thought there was a diameter to the fourth, what happened to it? You're correct, there was, but notice it's got a d squared down in the denominator. So that's what happened to d to the fourth. Two of those got canceled out. Okay. Now, we know what we used for VC, so we can go ahead and substitute that back in. And when we rearrange ourselves, we get this, the equation that I've boxed here. And this is called the Hagen-Poiseuille equation. And this describes steady laminar flow for a Newtonian fluid through a round pipe, or a capillary tube. Sometimes we think of it that way. So discharge can now be described as a function of the pressure drop that we could measure, the geometry of the problem, meaning the pore size in particular, or the tube size, the diameter, and the fluid properties. You can see that the viscosity of the fluid is wrapped up in there as well. One more extension, we derive that for a horizontal tube. And of course, we don't always expect flow to move horizontally. So what happens if we take that same exact study system and we tip it at some angle theta? And just for clarity's sake, theta is going to be the angle from horizontal, sort of taken in the direction of flow. So if we had flow vertically, we would think of a theta of 90 degrees. If we had flow vertically in the downward direction, theta would be 270. So you're always going counterclockwise, and you're doing so from the horizontal. So what actually changes when we do this, right? And I want you to think here about the summation of forces that we did. We had the pressure forces and the shear stress, but as soon as we deviate from horizontal, we're adding one additional piece, which is some component of the weight force, right? So now we've got some amount of the weight that is, I've written sort of x-directed here. It's acting in the direction of or opposing the direction of flow, right? So it's not an x-directed force, it's a flow-directed component. And without redoing the entire derivation, I just want to show you where this ends up showing up here, both in terms of velocity and in terms of discharge. So those look quite similar to equations that we've seen earlier in the derivation. What I want you to see here is that, instead of just delta P, we've got delta P minus the specific weight of the fluid times the length times sine theta. And so hopefully what you can see there is that the specific weight and the length term are getting you at the amount of fluid that's inside of that cylinder, and the theta is giving you the component of it that's acting along the center line of the pipe. Practically, what's happening, some of the delta P, some of the pressure drop is being accounted for by any changes in the actual geometry of the problem. So thinking about the elevation head that would be changing from one end of the pipe to the other. It's being offset somewhat from that delta P. Okay, Hagen-Poiseuille equation and a slight extension of it in case you've got a non-horizontal system. Hopefully that gives you a bit of a primer on how we think about laminar flow through tubes. All right, thanks everybody.